Hello everyone. In this video, we are going to understand the Beers-Lambert's law. In previous video, we have talked about the basic introduction of spectroscopy, electromagnetic spectrum, about UV spectroscopy, and its basic principle of electronic transitions. Another important concept in UV spectroscopy is the Beers-Lambert's law. And in this video, we will go through individually for Lambert's law, then Beer's law, and their logical combination, that is Beers-Lambert's law, its deviations and limitations. So let's get started. And first, let's see the Lambert's law. So in 1760, the Swiss mathematician and physicist John Heinrich Lambert observed that when a beam of monochromatic light, which is a light of single wavelength, passes through an absorbing medium, the intensity of transmitted light decreases as the distance traveled through the medium increases. Lambert's law considered only the effect of thickness or path length of the absorbing medium, and it assumes the concentration of solution remains constant. So basically, Lambert's law tells us the relationship between light absorption with the path length or thickness of the absorbing medium. So in this diagram, you can see when a beam of monochromatic light with its initial intensity I0 passes through a sample container or absorbing medium, it leaves the sample container or that absorbing medium in the form of transmitted light with the final intensity IT. And according to Lambert's law, this decrease or lowering of the transmitted intensity is directly related with the thickness or the path length. In other words, the absorbance by the sample is directly related to the path length of the sample container or absorbing medium. Here in these two figures, you can see the path length or the thickness of the first sample container is greater than the second sample container. And according to Lambert's law, the intensity of transmitted light is lower in case of first figure than the second figure, and the absorbance is greater in the first figure than the second figure. So the statement of Lambert's law is that the Lambert's law states that when monochromatic light passes through a homogeneous absorbing medium, the decrease in light intensity is directly proportional to the thickness or the path length of the medium. Okay, that means the decrease in the light intensity is directly proportional to the thickness or the path length of the absorbing medium. In other words, we can say that absorbance is directly proportional to the thickness or path length of the medium. That means absorbance is directly proportional to path length. Capital A is directly proportional to L. Next is the Beer's law. In 1852, the German physicist August Beer proposed that the amount of light absorbed by a solution depends not only on the path length but also on the concentration of the absorbing species. Beer demonstrated that increasing the concentration of absorbing molecules results in greater absorption of light. So, in simple words, Beer stated the relationship of absorbance with the concentration of absorbing molecules. So, in these below figures, you can see in the first figure there is high concentration of absorbing molecules. In the second figure, there is medium concentration of absorbing molecules, and the third figure there is lowest concentration of absorbing molecules. So according to Beer's law, the absorbance will be higher in first figure than the second figure and then the third figure. So what is the statement of Beer's law? So Beer's law states that when monochromatic light passes through a solution, the absorbance is directly proportional to the concentration of the absorbing species, provided the path length and wavelength remain constant. So mathematically it can be written as absorbance is directly proportional to concentration. Capital A is directly proportional to C. And after logically combining both Beer's law and Lambert's law, we get the combined Beer-Lambert's law. So Beer-Lambert's law is a fundamental principle of UV visible spectroscopy, which establish the quantitative relationship between the absorbance of light and the properties of solution. So it combines both Lambert's law that describes the effect of path length and the Beer's law that describes the effect of concentration on the absorbance. So since according to Lambert's law, capital A, that is absorbance, is directly proportional to the path length L. According to Beer's law, capital A, that is absorbance, is directly proportional to C, that is concentration. And according to Beer's-Lambert's law, absorbance is directly proportional to LC, that is path length and concentration. And when we replace this proportionality sign, we get an proportionality constant, that is epsilon, which is nothing but the molar absorptivity, or also known as molar extension coefficient. And hence we got capital A is equals to epsilon LC. Capital A, that is absorbance, epsilon, that is molar absorptivity or molar extension coefficient having unit liter per mole per second, L, that is path length of the cuvette or sample container in centimeters, and small c, that is concentration of the absorbing species, mole per liter. Now we have to see the complete derivation of Beer-Lambert's law. So let's get started. So in the left hand side you can see the mathematical steps, and in right hand side you can have the explanation if you need. So let's start from the first step. So here you can see minus di is directly proportional to I dot c dot x. So what is this minus di? The minus di means the small decrease in the intensity. Small decrease in the intensity, it will be directly proportional to the I, that is intensity of light at that point, C, that is the concentration of the solution, and the dx, that is the small thickness of the layer, that is dx. Next, when we introduce the proportionality constant k in this equation, we got minus di is equals to k, that is proportionality constant, dot I dot c dot x as it is. In next step, when we take out this I to the left hand side, it will go to the denominator, and we have got minus di divided by I is equals to k dot c dot dx. In next step, we just have to shift this negative or minus sign to the right hand side. So we got di divided by I is equals to minus k dot c dot dx. Next, we have to perform the integration. So by integrating both sides, we get this equation. So integration of di by I, upper limit it, lower limit I 0, is equals to integration of minus k dot c dot dx, upper limit L, lower limit 0. So we just have to integrate both sides when x is equals to 0, I is equals to I0, and x is equals to L, and I is equal to IT. So what is this x is equal to 0 and I is equal to I0? So when the path length or thickness is 0 and the initial intensity is I0, and x is equals to L and I is equals to IT, means the when incident light passed fully through the sample container, and the IT is nothing but the final intensity of the light. So when we simplify the integration, or we get the ln, that is natural log of I, upper limit IT, lower limit I0, is equals to minus kc, which is out of integration as they are constants, and in bracket x, upper limit L, lower limit 0. So after applying the limits as upper limit minus lower limit to this equation, we will get next step, that is ln it minus ln I0 is equals to minus k dot c dot L. That is when we apply limit in this side, we will get upper limit minus lower limit, that is ln it minus ln I0 is equals to minus kc. So L minus 0 is nothing but L. Next, in the next step, when we follow a mathematical rule, that is ln A minus ln B is equals to ln A divided by B. So here ln IT minus ln I0 is nothing but ln IT divided by I0. That equals minus K dot C dot L. If we have to remove this minus or negative sign, we just need to shuffle this reciprocal. So when IT goes to denominator and I0 goes to numerator, this negative sign will be disappeared. So ln I0 divided by IT is equals to K dot C dot L. So in the next step, so this is our final step of previous slide, that is ln I0 by IT is equals to capital K dot C dot L. And after converting this natural log into log to the base 10, we got 2.3026 log to the base 10 I0 by IT is equals to KCL. When we rearrange the equation and shifting this value to the right hand side, we got log to the base 10 I0 by IT equals to K divided by 2.3026 dot C dot L. Here, the K divided by 2.3026 is nothing but the value of epsilon. That is our proportionality constant, which is nothing but molar absorptivity. And at the same time, the this the value of this term, that is log to the base 10 I0 by IT, is nothing but the absorbance. That is the logarithm of ratio of incident to transmitted intensity. And after substituting the values of epsilon and absorbance here, we will get the final Beer's-Lambert's law, that is capital A is equals to epsilon dot C dot L. So I hope you are clear with the derivation of Beer's-Lambert's law. Next, we have to learn about the different deviations and limitations of Beer's-Lambert's law. So, what is mean by a deviation? So, a deviation from Beer's-Lambert's law occurs when the linear relationship between absorbance and concentration is no longer maintained under experimental conditions. So, ideally, the Beer's-Lambert's law says that the absorbance should directly proportional to concentration. But when there is disturbance in this relationship, that condition is known as the deviation. So, there are three types of deviation: the real or fundamental deviations, chemical deviations, and the instrumental deviations. So the first one is the real or fundamental deviation. So it occurs at the high concentration, generally greater than 0.01 molar, where molecules come close to each other and results in intermolecular interactions, changes in the refractive index, alteration in molar absorptivity epsilon, etc., and thereby no longer existence of Beer's-Lambert's law. Next is the chemical deviation. So these deviations occurs due to the chemical changes such as ionization, association, dissociation, complex formation, acid-base equilibrium, etc. Example, the chromate and dichromate ions. Both ions exist in equilibrium in the solution, and since both chromate and dichromate ions absorb light differently, the major absorbance deviates from the Beer's-Lambert's law, and hence it is called as chemical deviation. The third is the instrumental deviations. So these deviations arises due to the imperfection of the instrument. We can say the instrumental errors. Examples: use of polychromatic light means the light with different or multiple wavelengths instead of monochromatic light. Then presence of stray light, detector instability, wide spectral bandwidth, improper wavelength selection, etc. Next are the limitations of Beer's-Lambert's law. So a limitation is a practical condition under which Beer's-Lambert's law cannot be accurately determine concentration of the substance. The law provides accurate results only when all its assumptions are fulfilled. The major limitations of Beer's-Lambert's law include: first, it is only applicable to the dilute solution, because as we learned in the derivation, that is high concentrated solution exhibits the molecular interactions causing the deviation from the linearity. The second limitation is the requirement of monochromatic light. So the law is only valid when the radiation consists of single wavelength, that is monochromatic light. Third deviation is homogeneous sample. So any suspended or colloidal particle can scatter light, which can affect the absorbance measurements. Next, fourth deviation is the chemical instability. So, if absorbing species undergoes ionization, association, dissociation, or complex formation, it can affect the measurement of absorbance. And the last limitation is the instrumental errors, such as stray light, dirty couverts, improper calibration, detector noise, etc. And they can reduce accuracy of measurements. So I hope you understand what is Beers-Lambert's law, its complete derivation, and its deviation and limitations. So thank you for watching the video.